Now, another thing we'll say what is called the independence. Okay. So you see, what is the meaning of independence? So when we say that two events A and B are statistically independent, that means, can you tell me if two events A and B are statistically independent, then what will happen to probability of A slash B? This one you have to say.
It will be probability of A.
Yes, definitely, because A and B are statistically independent. So whether B has occurred or not, it does not make any sense. It will be directly probability of A, because A and B are independent. So if B occurs, that is fine, but it does not change the probability of A because they are independent. Okay, very good. So now if you say, similarly, if I can write probability of B given A will be equals to probability of B. So we can write if such thing. So probability of A and B, or A intersection B, or joint probability, will be equals to nothing but probability of A and probability of B. This you used to see. Okay. So in definition we say that when two events A and B are statistically independent if and only if I write I double F, that means if and only if probability of A comma B will be equals to probability of A into probability of B. Okay, so probability of A comma B, that means joint distribution, will be the multiplication of independent. Similarly, if B, A, B, C are, there are three events which are mutually independent. A, B, C, three events which are mutually independent. We can definitely say probability of A comma B will be equals to probability of A into probability of B. We can say probability of A comma C will be equals to probability of A into probability of C. We can say probability of B comma C will be equals to probability of B into probability of C. And we can tell if it is probability of A comma B comma C, that will be nothing but probability of A into probability of B into probability of C. That's all. Okay. So if all the events A1, A2, A3 dot dot AN are independent for any subset, we can call probability of A1, A2, A3 dot dot AN will be equals to probability of A1 to probability of A2 dot 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 probability of AN. That is the whole thing. Okay. Is it fine to everybody?
Yes, sir.
Okay. Now next subsection will move. Very important concept. Bayes theorem is very important. 1.1.4 we are moving very fast. 1.1.4 it will be random variables, or rather I should say it is a discrete random variable. Very important concept, discrete random variable. 90% students bear misconception about the random variable. Okay, so let me describe. So definitely all of you may have the correct conventions or correct concept. So suppose we are doing some experiment. Let's say any experiment, rolling a die, tossing a coin, this, that. and you are getting a outcome, which is an event. Okay, so you have the experiment, you have the outcome, which is random, but still you don't have the variable. What does it mean? What does it mean you don't have the variable? Again I am coming. So a random variable means, suppose you are doing experiment, you are getting outcome. Suppose you are doing experiment of rolling dice, you are getting outcome of either getting 1 or 2 or 3 or 4 or 5 or 6, but still that is event. That means I am getting 1, I am getting 2. No number is associated with that. So still you are in the event. But if you assigned a variable, that means a real valued number associated with the event or the outcome of the experiment, so your experiment outcome will vary, so those number also will vary, and those numbers will be called as the random variable. Let me write again, I will explain, because this is the most fundamental concept. If you don't understand this concept, you cannot proceed, you will be lost here. Okay, so discrete for the timing, don't bother, just random variable you try to think. RV will call to you real function of the element of a sample space So a random variable is a real valued function of the elements of a sample space S in some experiment E, which maps each possible outcome zeta, which belongs to sample space, to a real number x zeta as specified by some rule. What I am trying to say? So a random variable is a real valued function of the element of the sample space. So suppose we have a sample space, this is sample space S, which maps, so there is some function which maps all the element of the sample space, which maps all the element of the sample space. So zeta I is the element of the sample space, maps all the element of the sample space in a real number, So that is called the random variable. The variable of this real number x zeta, real number x, which is a function of zeta, is called the random variable. So is it clear? I am trying to give some example. Suppose we roll a die. So what is our sample space? Our sample space is consist of an event A1, which is getting 1, an event A2, which is getting 2, an event A3, which is getting 3, an event A4, which is getting 4, event A5, which is getting 5 number, and A6, which is getting number A6. Now, suppose I form a function, okay, which called that whatever number we receive, we square it, okay, and then we get the real number. So suppose 1 we receive, we square it 1, we get 1. 2 we receive, we square it, we'll get 4. 3 we receive, we square it, we get 9. Similarly, all the number we get. So we get a set of real number and a variable which is a function of zeta. This is s, this a1 a2 all are zeta element, and this variable is called a random variable. Okay, now tell me your doubt. This is a very vital concept. If you don't understand, you ask 100 times, but if you don't understand, we don't move, because we cannot do anything if we don't understand random variable. Okay, tell me, is it making any sense whatever I speak? Midul?
Yes, sir. It is. You can put.
Is it fine?
Yes.
Okay, Jafar?
Yes, sir. You can proceed.
Okay. So, and is Hatipriya? Are you there?
Yes, sir. Yes, sir. No problem, sir.
Do you understand?
Yes, sir.
Okay. See, the most of the student don't understand the random variable. They always think that this die example, I should not give this die example. And in most of the book, this die example is given, and it is says that 1 means 1, 2 means 2, 3 means 2. It does not require. So any function, if you can do square root also, you can do square, you can do anything. So any function, and this 1 2 is number is coming for the die. That is what confusion is building. Okay, that is what confusion is building. Suppose we make another thing. Suppose we do head and tail. Okay, so h and t, and then we say that we map a function which map h for 100 and tail for -100. So this is a function. Okay, so you see, we map the event to a real number line. When we map the event to a real number line by means of a function, by means of a real valued function, then the variable we get out of the function is the random variable. Okay. Is that fine?
Yes, sir.
Okay. So now, if we call discrete, that means that we have a discrete number. For example, I said that 1, 2, 3, 4, 5, all those things, and then we square it. So we get a discrete number. So all the numbers are not possible here in the real line. So we call this a discrete random variable. If all the numbers we map such a way that we get a continuous series of number, that becomes a continuous random variable. Okay. So this is the case. So then what is our random variable becomes? So x is our random variables. How we get the x? So x is our random variable. How we get the x? When we map f of zeta. Zeta means xi, f of xi. Xi means when you map f of xi, that means xi means element in the sample space. Whatever the event, all the elements in the sample space, when you map it, all the possible event, when you map it, we get a random variable. Okay. So the value of the random variable depends on the function, the way we are mapping, and the numerical value and the outcome of an experiment. Okay, so zeta is the outcome of the experiment, f is the function. So random variable depends. So random variable is the outcome of the experiment, which is zeta, and the function. Both the cases it depends, right? So here we say that discrete random variable, that means we focus on the random variable that can take some discrete value, not the continuous value. Then we call it is a discrete random variable. Okay. So now this is very important writing. Let's say I write probability of x equals to small x. What does it mean? It means x is a random variable and small x is number, particular number, some number. Okay, that means what will be the probability when of the random variable having the number small x? This is the meaning. Okay, don't confuse. Don't confuse. X, capital X, always I will follow the same notation. Everybody follows the same notation. Capital X is means the variable, small x means the number. Okay. So this is the concept of. Can you give any example? Other example of a random variable getting random variable? Anybody? Jafar, can you give it?
Yes, sir.
Any other example? I gave two simple example how the random variable comes from the sample space. Can you give any other example?
Mm, mm, so can we model everything to real number? Like if we take the example of cards, can we map
Yes,
that as
everything. So you have to map it to the real number. Otherwise, you will not get the random variable. You take the cards. You tell the cards example.
mm, okay, if we take the example of cards, for example, a card is drawn from a deck. Then if it is a spade, then we can map it to some number. Let's assume 10. If it is a heart to 20, if it is a club to 30, and the other.
Yeah, so that way you could map in a number. So the way you will map in a number, it's not fixed. Anybody can map in another way. Okay. So you are saying 20, I can say the 200, or I can say something else. But there must be a functional form that if I get this event, this function will transform this event to a number. Okay. Then only it is valid. Okay. So you should not get confused with the random variables. So now the concept should be clear, right? And random variable cannot be imaginary number, although you will see in advanced literature there are imaginary numbers, distribution and all, but for the time being you assume that it should not be imaginary number, it's a real number. Okay, it can be positive, it can be negative, but it's a real number. That's what it's called, a random variable. So now with this definition, we'll go to random PMF, probability mass function, and I'll explain what does it mean, probability mass function. So we cover a lot of things today. So it's a probability mass function. It's also a very important concept, PMF. Now we have a sample space S, we have a event zeta I, and we map this event in a real number space. So this is the random variable x equals to f of zeta. Now with every event there is associated with a random variable one-to-one mapping, and those event has some probability of occurrence, right? Probability of occurrence. So ultimately what we are getting? We are getting a number, one dimension we are considering, we are getting a number which is coming out from the sample space after applying the function, and we have the number having some probability. So this is probability, and definitely the probability of all number will become sum of all number will become 1. Okay, so this distribution, that means probability associated with the random variables, is called the probability mass function. Okay, suppose I give one example. I said that the event can be 1 can come, which is called A1, 2 can come out of dice rolling, 3 can come A3, A4, A5, A6, and I said for 1 it is 1, for 2 it is 4, for 3 it is 9, for 4 it is 16, 25, 36. So random variable value we have 1, 2, 1, 4, 9, 16, 25, 36. And what is the probability of getting 1 random variable? It is 1 by 6. Probability of getting 4 is a random variable, it is 1 by 6. Probability of getting 9 is also 1 by 6. Probability of getting 16 is also 1 by 6. Probability of getting 25 is also 1 by 6. 36 is also 1 by 6. So this full distribution is called the probability mass function. Okay, so if we define, what will be the definition? Probability mass function, PMF, we call it as P of x small x, okay, of a random variable x is a function that assign a probability to each possible of the random variable x. So when we assign a probability, so when some event occurs, we assign a random number and it has probability, so we assign that probability with that random number. So we have a random numbers, we have all probabilities associated with the random number, and that is called the probability mass. Okay, is it correct? Do you agree? Everything is you understood? So we explained lot of concept. Okay, so probability mass function is also a very good concept. When we have a discrete distribution, probability mass function is extremely important because we don't have probability distribution function there. We have the probability mass function. So what will be the probability mass function properties? Sorry, properties will be probability mass function will be, as it is a probability, it will be in between 0 and 1, and sum of all probability mass function will be equals to unity. Now tell me, do you understand this?
Yes.
What others say?
Yes, sir. No problem.
Yes, three very important concept we described. One is Bayes theorem, which is very important concept, and there is random variable, which is very important concept, and probability mass function is also very important concept. Okay, so now you should not have a slight confusion about these three. Okay, otherwise you could not proceed. That's what I am emphasizing clearly. Tejaswini, is it fine to you?
Yes, sir, it's absolutely fine.
Okay. Okay. So the pace I am moving, is it okay? Because it is brass up, that's what I am going a bit quicker.
Yes, sir, it's okay.
Okay. Now, there are few well-known probability mass function that we will discuss. For example, Bernoulli's. People may ask, okay, you have done a stochastic random process course, you have, which is a very advanced level course, And do you know that Barnard is first we will move to Barnard is random variable and how we can model it. So Barnard is subject is actually very important and interesting subject. I don't know students don't get interest. So initially when I was thinking to flow this, I thought there will be 50 students, but we have very small class anyway. That is good for us. Okay. So Barnard is random variable. What is that? So suppose we have a random variable and the simplest possible may be 2. Okay. I am giving some example. Suppose we consider that a football match, a final football match, is a outcome of it is a random variable. So then what may be the outcome? Either I mean there is draw is not possible. Okay. So suppose I am playing the final match. So either I win or I lose. So there are two outcomes. Suppose I am flipping a coin. So there are two outcomes, either head or tail I will receive. Suppose I am sending and from my sensor to my data processing unit. Suppose I have a sensor mounted on field and from there I am sending the measurement. You know, if I send the measurement through the network and all, measurement may be lost. So if I am here, my sensor is at the field or some airport or somewhere, and from there I am receiving measurement. So at some instance, one, the sensor send the measurement, I may receive or I may lose. So the outcome is 2, either receive or lose. So like that, there are many examples where there are only 2 outcomes. Okay. So if there are 2 outcomes, pass or fail, win or lose, head or tail, that means we have random variables, only 2. So we can model those things with the 2 random variables. Okay. Oh, sorry, my battery is running low. Okay, I make it. So this is the simplest distribution, Barnard's distribution. Here we have 2 possible outcomes. So the main takeaway, what I am trying to say, it has 2 possible outcomes. It has 2 possible outcomes. So this experiment, which has the 2 possible outcome, is generally called the Bernoulli's trial, and the resultant random variable is called the Bernoulli's random variable. Okay, 2 outcomes. So the random variable is called Bernoulli's random variable. Okay, so generally it's most common to associate the random variable with 0 or 1. So 1 I exam 0. In the 1 I lose the match 0. I receive the measurement, I measurement. So generally 0 and 1, these 2 outcomes it's associated. And so if x is the random variable, that's what I'm trying to say. Px, probability mass of getting 0, or rather 1, I win or not. That is a number, let's say small p. So what will be px of get 0 variable? That is a small p. Suppose I coin a toss. So that is a random variable, Bernoulli's variable. So we map that. Suppose we get a head, we map it as x equals to 1. We get a tail, we map it as x equals to 0. Similarly, so in this case, what in case what is the probability of getting 0? Half. But always the event 1 and 0 are not equally probable. Suppose India is playing football with Brazil or say China. So then the win or lose will not be equally probable, right? Lose probability of lose will be very high. Okay, so always we take the probability is equal, but that is not always in the real picture. Okay, if we have a very good network, probability of getting measurement means 1 will be very high. lose will be very less. So that's what I say, that probability of getting 1 is P. That means it should not be half. But if it P will be half, then getting it or tails, that will go on minus half. But always it is not to be. That is what I consider it as a P. So now you see how our probability mass function becomes. Probability mass function becomes only 2.0 and 1, and 0 has the probability, 0 has the probability of 0 has the probability of P, sorry, 1 minus P, and getting 1 has the probability P. Okay, both are unknown. So this is a kind of bar knowledge random variable. It is very useful and very useful in modeling many real system. For example, we work a couple of years back where we try to model a delay coming out from the sensor through the network, and we model it using bar knowledge when the packet is dropped. So important concept, and this is a PMF is very simple, P and 1 minus P. Okay, so there are other random variables. Okay, any query up to this?
Sir, I have a doubt that any example in physical world that only two events and probability is not half.
Yes. Any example you want?
Yes, sir.
That's what I gave the example. Na? So suppose you are receiving a measurement through a network. So one packet has sent from one computer and it need to reach to a computer through a common network. So it's not like that 50-50 chance, na? That whether you will receive or not. So if the network is very good, the chance of receive, so P will be more than 0.5. If network is very bad, okay, chance of receiving will be very poor. It could be even less than 0.5.
Okay, sir.
So yeah, so getting half is a very rare event which we get while we toss a coin. Okay, that is not in the reality. Always we have probability of win and probability of lose. It's not always half and half. Okay, that's what I said, that if you play football, if you get in play football with any other team, anything, China, Japan, whatever, so probability of win will be very less. It's not half, right? So half is a mere coincidence which happened for tossing a coin. Okay.
Okay, sir.
Anybody? Yeah, anybody? Okay, today lot of things I discussed, right? Very quickly. It's kind of capsule. Okay, so now I will go a little bit slower because these basic things which might be very boring, those who know it, is over. This is required for the completeness. Now I'll go a little bit slower, definitely, and it will be helpful to you also.